Ion dipole forces are attractive forces between an ion and a polar molecule. An ion is a particle that has a full electrical charge, such as sodium ion Na+, or chloride ion Cl-. A polar molecule is a molecule that has two different ends, which is one side with a partial positive charge and the other side with a partial negative charge. So, in ion dipole forces, a fully charged ion is attracted to the partially charged end of a polar molecule. Because one side has a full charge, this attraction is stronger than normal dipole-dipole forces. Next, let's look at what is needed for ion dipole forces to occur. Two things are required. First, an ion, which can be either a positive ion, which is a cation, and a negative ion, which is an anion. Second, a polar molecule, which has a permanent dipole. If there is no polar molecule, then ion dipole forces cannot occur. Now, let's see how ion dipole forces work. First case, positive ion, also called a cation. For example, sodium ion in water. Water is a polar molecule. In water, the oxygen atom has a partial negative charge, and the hydrogen atoms have partial positive charge. Since sodium ion is positively charged, the partial negative charge of oxygen side of the water molecule will point towards the sodium ion. This creates an attraction between them. Many water molecules will surround the sodium ion, forming what we call a hydration shell. Second case, negative ion, also called an anion. For example, chloride ion in water. Since chloride ion is negatively charged, the partial positive charge of hydrogen side of the water molecule will point toward the chloride ion. Again, water molecules surround the ion and form a hydration shell. Now, let's talk about why ion dipole forces are important. One major reason is dissolving ion compounds. For example, when sodium chloride and ACl dissolve in water, the compound separates into sodium ion and chloride ions. Water molecules then interact with this ion. Sodium ion interacts with oxygen side of water, chloride ion interacts with hydrogen side of water. This ion dipole attraction stabilizes the ions in solution, allowing the salt to dissolve. However, if the solvent is nonpolar, such as methane, ion dipole forces cannot form, so sodium chloride will not dissolve. Next, let's look at what affects the strength of ion dipole forces. The first charge is ion charge. Ions with higher charge create stronger dipole forces. For example, magnesium ion attracts more strongly than sodium ion. The second factor is ion size. Smaller ions produce stronger electric fields, so they attract polar molecule more strongly. The third factor is the dipole moment. The more polar the molecule is, the stronger the attraction will be. Now, let's briefly discuss the energy concept. For an ionic compound to dissolve, two energy changes occur. First, energy is required to break the ionic lattice that hold the ions together in the solid. Second, energy is released when ion dipole forces interactions form between the ion and the solvent molecules. If the energy released from the hydration is large enough, the compound will dissolve in the solvent. Finally, let's look at some real-life examples of ion dipole forces. The examples include sodium chloride in water, potassium nitrate in water, calcium chloride in water, and electrolytes in the human body. Lastly, It is important to remember that ion dipole forces are intermolecular forces. They are not the same as covalent bonding, ionic bonding, or hydrogen bonding. That's all from us. Thank you.